Can people hear me okay?
Oh, yeah, we can.
Cool. Carson, you've got your camera on. I don't know if you knew. Oh, there it goes. I'm told that when people turn the cameras off, it somehow saves bandwidth. I don't know if that's true or not. Welcome to another exciting digital design class. So it's a snow day. Snow, yay, snow, yay. But distance learning means there are no snow days. So we'll have, the learning will go on because everybody presumably is safe at home and you don't actually have to go anywhere. And therefore, there's no danger of anyone tripping and falling. Somebody said something about how do I do question 36? I forgot who asked me this question. Is that person here in the audience? Does anybody have any question about question 36, homework 1? Okay. Does anybody have any questions about homework 1, which is due tonight? No questions. All right. So I've posted homework 2. It's due next week on Monday. And I thought what I would do is cover some of the material that's in homework 2. And maybe you guys would ask me questions about it as well. So that'd be good. That'd be good. So one of the things that you can do with AND gates, in case you want to do things with AND gates, and we will in this semester do things with AND gates. We'll do things. So here's an AND gate, and then here's another AND gate, and now here's a third AND gate. So we took all the AND gates and we wired them up. Now it looks like if you assert A and B, the output will be a 1. And that's because that's how AND gates work. You have to have both A and B on in order for the output to be asserted as true. Why? Why is that? Why? Well, because it's switches in series, right? Switches in series. How do I make the light bulb go on? I have to complete the circuit. This is a battery, by the way. So to complete the circuit, it's not enough that I turn on A. I got to turn on B. I got to turn on C. I got to turn on D. A, B, C, and D all have to be 1. Everybody agrees that every single switch has to be closed before you complete the circuit and the switch goes on. So if I turn the switch D on and off, when I turn it off, the light goes off. When I turn it on, the light goes on. Light goes off, light goes on, light goes off, light goes on. Okay, so then here comes the AND gate equivalent of 4 switches hooked in series. I have to have all A, B, C, and D all asserted as 1. The output here will be a 1. The output here will be a 1. These two 1s will be used as input to the final gate, and then the output will be a 1. So it's clear. A, B, and C all have to be 1 in order for F to be 1. Now you can take this whole rigmarole and rewrite it as a single 4-input AND gate. And the same rule applies. A, B, C, and D all have to be 1 in order for the output to be 1. Does everybody kind of see that? Is anyone confused by that? So I got to say, the last class was really confused by this. And you can.
Do you mind saying that one more time?
Sure. A, B, C, and D all have to be 1 in order for F to be 1. Just the same as switches A, B, C, and D all have to be on in order to complete the circuit and make F light up. F is your light bulb. Does it sort of make sense? Having more switches doesn't change the behavior. Everybody has to be on for an AND gate to output a 1. So if you have a 4-input AND gate, F is equal to 1 if and only if A, B, C, and D are equal to 1. If any one of them is equal to 0, F will be 0. Why? Because if any one of these switches is off, the light will not have a complete circuit. It won't light up. Moreover, if you write it, it's A times B times C times D. Now, if any one of these things is off, they represent 0, and 0 times anything is 0. So it's clear. You can't multiply by 0 and expect anything other than 0 because, because that's what 0 does. It makes things 0 when you multiply by 0. I don't know how else to say that. It's an operation with 0 and 1, according to the book. In other words, multiply by 1 and you get back the original thing. That used to be called the identity theorem, but now they're calling it operations with 0 and 1 in the book. I don't know why. And if you multiply by 0, it makes things go to 0 because I don't know, multiplying by 0 makes things 0. I learned math on the street, and this is what I know about math. If you multiply by 0, things go to 0. Don't ask me why. It's like a law or something. I don't know. So here comes an 8-input AND gate numbered 0 through 7. And an 8-input AND gate says if any of the inputs are equal to anything other than 1, the output is going to be 0. It's just like having 8 switches in a row. Doesn't matter how many switches you have, they all have to be on to complete the circuit and make F equal to 1. Anybody have any questions about that? Am I kind of sort of clear on that?
So, Professor, if it was like a bunch of OR gates, only one would have to be equal to 1, right?
Okay, OR gates work differently from AND gates.
Right.
Yeah, so we haven't talked yet about OR gates. Let's do the OR gates. OR gates is the difference between AND gates and OR gates is the difference between series and parallel. So now I don't need any switch to be on. I just need a switch to be on. Doesn't matter which one. As long as any one of them is on, the output is going to be a light that lights up. So if I have 3 switches, A, B, C, and D, all in parallel, doesn't matter which one's on, as long as one of them's on, the output will be 1. That means the light is on. So you can have, here's an OR gate with 4, and anything that's ORed with a 1 is going to be a 1 because parallel, right? Because parallel. And the way you write it is A or B or C or D, and anything ORed with 1 is equal to 1, and therefore F will be 1 if any one of these things is 1. And that's the nature of parallel versus series. Is it clear now? That's clear, right?
Yeah. One more thing. Can you have a combination of and OR gates? Like so.
Sure. Yeah, absolutely.
Okay.
Absolutely. You can combine and OR gates. In fact, we will clearly want to do that later on in the in the course, if not even in this class. But for now, let's just focus on either AND gates or OR gates.
Okay, thank you.
Yeah. So then there's the question of implementation. Implementation is important. For example, here is an implementation of a 4-input AND gate, and it has a basic truth table of a 4-input AND gate, just like this one. But its behavior is different because this gate takes time to compute, and that gate takes time to compute. And if you call the time it takes to compute a gate delay, then it takes 2 gate delays before F is asserted as being correct. So if you change the input, you got to wait 2 gate delays later. How long is a gate delay? Well, if it's a 7400 TTL dog breath stockroom chip, you will have to wait 17 nanoseconds. Okay, it's not terribly long, but it's not infinitesimal. Well, actually, it is kind of small, but in fact, 17 nanoseconds per gate times 2 gates, you got to have to wait, I don't know, 34 nanoseconds before you get F. Whereas if you used a 4-input AND gate, you could save a whole 17 nanoseconds. So that's kind of cool. Depends on the implementation. Different circuitries will behave with different rates.
So the number of inputs into a gate doesn't affect the time. It's just
No.
the number of gates.
Is the number? Yeah, that's right. The layers, the number of layers. So we do the same thing for 3-input AND gate. Here's A and B. Now we add another gate and we make C. And in fact, this also takes 2 gate delays, but the 3-input AND gate by itself only takes 1 gate delay. So that's kind of an interesting thing. We say this takes 1 delta T, whatever delta T is, gate delay, change in time. So that's cool. That's cool.
Does the type of gate change the gate delay, or is it still the same?
Yeah, sure. The type of gate does change the gate delay. So if you go to advanced, there's 7400. There's 74S00. That's Schottky. That's faster. There's 74HC00. That's a high-speed CMOS variant. There's 74LAS00. That's a low-power advanced Schottky gate, and that goes a little faster. There's all kinds of variants. They all have the same pinouts, but internally they're implemented differently and they draw different power. So if you're going to stay within a family of high-speed CMOS, you'll be fine. But if you mix high-speed CMOS with the old style 7400, the fan out will change. Fan out refers to how many inputs an output can drive. Usually we like to be able to drive as many as 10 inputs. Each time you drive another input, it takes a little current. Well, it takes a lot more current to drive 7400 than it does to drive 74HC00. Plus, the high-speed CMOS doesn't have the current capability to drive 10 of the 7400 inputs. So when you start mixing families, things get complicated. But that's just, that's an implementation nuance. Here's another way you can build a gate. Here's an electromagnetic thing called a relay. You close this switch here, it energizes that coil and makes this clapper come down. Now that doesn't work very fast. That works in hundreds of milliseconds, not nanoseconds. So now you've got a completely different implementation of a switch. It's now an electromagnetic device. And because it's not an electronic device, it runs orders of magnitude slower. Nanoseconds versus milliseconds is times 10 to the minus 9 versus times 10 to the minus 3. 6 orders of magnitude slower, 1,000,000 times slower. This is 1,000,000 times slower than a transistor, but this is what they used for building the first generation of digital computers, because all they had for the Mark I in the Harvard sequence machine, the ASC they called it, were relays. The Conrad Zuse machines all built with relays. They didn't try and do it with tubes, and they found that the relays were just very convenient. They had them, they were reliable. The phone company was building all of its phone switch networks with relays, so there were a lot of them available. And you could still build switching control systems with relays. In fact, when you go to an elevator control room, you'll see that they built a finite state machine with relays because relays are reliable and they could switch high current. So then if you had a 3-input AND gate, clearly series, all of them have to be on for the output to be a 1. And there's a little delay. Here's some fraction of a second or fraction of a gate delay, and then the output can change. So that's that. Now we have an idea about, I guess we'll call it creating networks of gates. Creating networks of gates. Any questions about this? So then here's a question for you guys. I mean, this is how many different possible inputs could there be if you have an 8-input AND gate? What are all the different combinations with an 8-input AND gate? What kind of a truth table? How many rows in the truth table do I need?
When you need 256.
Yep, 2 to the 8. That's correct. So if a 2-input AND gate needs 2 to the 2 or 4 rows, that's 0 through 3, then a 3-input needs 2 to the 3, which is 8 rows, that's 0 through 7, and 2 to the 16, or 2 to the 8 rather, is going to be 256. So that's a long, you don't want to write a truth table with 256 rows in it. You're better off writing a program to generate it. So this is a sort of a summary of how the OR gate works. And now you can see the OR gate with 4 inputs, and then you could see the OR, the Boolean algebraic correspondence to that gate. And question 8, let's look at question 8. In homework number 2, let's have a looky-loo and see what I can see here. Question 8. Question 8 says, which of the following equations represents a 3-input OR gate? Well, there it is. It's a 3-input OR gate. And so that's clear. And then question 10 says, I'm skipping around a little bit, but not too much. What is x or x prime equals 1? Suppose x or x prime equals 1. That's a theorem. What theorem could that be? This is question 10. Well, in case you're ever wondering, you can always look these things up. Go to page 51 in your book. I think I can find page 51. Here's page 51. So I'm looking for x or x prime equals 1. Where could it be?
Theorem of complementarity.
There you go. There you go. So the theorem of the complementary, or theorem of the complementarity. I guess the theorem of the complementary would be something like, oh, it's always nice to say good things to people, right? It's like you complimenting them. That's a theorem of the complementary. Whereas the theorem of the complementarity, that's when x or x prime equals 1. And here comes the dual. And notice the dual is written over here with the d's. And what's the difference between the dual and the non-dual for the theorem of the complementarity. Well, ones got changed to zeros. Zeros got changed to ones. Plus got changed to times. Times got changed to plus. And the variables are left alone. Now, is it true? Well, let's see. If x is equal to 1, 1 times x prime must be 1 times 0, and that's 0. If x is equal to 0, 0 times x prime is 0 times 1. 0 times anything is 0. So that must be true. And if that's true, then this must be true over here. And that says if x is equal to 1, then x prime must be equal to 0, and 1 or anything is 1. 1 or anything is 1. Theorem of the complementary. And in fact, you get that with operations of 0 and 1. 1 or 1 is equal to 1. And the dual of 1 or 1 equals 1 is x and 0, or x times 0 is 0. And that should feel appealing to you because multiplying things by 0 makes things 0. So that's okay. I like that. Multiplying by 0 is 0. Multiplying by 1 is like the identity, right? Multiplying by 0 makes it 0 because I don't know why. Because that's how math works. When you multiply by 0, it becomes 0. I don't know. That's a snide answer. But it's true. All right, because when you multiply by 0, it's 0. And we don't actually ask why that's true. Why is that true? If you multiply by 0, it's 0. I think if we asked why that's true, when they kick us out of the classroom and they say, why are you asking these hard questions? I don't know why that's true. But that's just how they've defined the algebra. How's that? By definition, multiplying by 0 makes things 0. Is it true? Does multiplying by 0 make things 0? The answer is maybe. If you're a quantum computer, maybe not. If you're a normal computer using standard algebra, then yes, it does. So forgetting for a moment that they have these things called quantum computers, because I really don't know much about them, but I do hear they're kind of cool and we should get one, but I don't know. They're kind of cold or something. Let's do an example of De Morgan's theorem. Here's De Morgan's theorem. AB anded together, inverted, and we now write it with apostrophes. Now you could have rewritten this equivalently. You could have wrote A bar or B bar, but I think the book has been using parentheses, apostrophes. So AB apostrophe is equivalent to AB with the bar on top. So you can write it either way, and you'll find other books that write it that way too. But this book, I think he doesn't really use the overbar notation very often, if at all. And that's okay. That's all right. So here's De Morgan's theorem. How can I prove that it's true?
You can maybe take the dual of it just to check.
You could do, sure, you could do the dual. All right. So you're saying AB inverted equals A prime or B prime. So let's take the dual. I like that. Why not? Take the dual. So if I take the dual, times goes to plus. So that says A plus B inverted must be equal to A prime and B prime. That's the dual. So this is the dual of that. And both are correct. And both are in different forms. But wait, if you use De Morgan's theorem here, you distribute the A and B prime inside and you change the plus to times. And sure enough, you get that. If you use De Morgan's theorem in here, you distribute the apostrophe into the A prime or the B prime. And if you take this expression, you can write it in terms of gates. So A, B, ORed goes into an inverter to make F. That's A or B inverter. Or you can have A, B inverted go into an AND gate. And check it out. These two networks of gates look really different, but they are equivalent according to the equation. Equivalent. The other thing you can write is A inverted goes into an OR. So this is equal to A prime or B prime. We can call that G. And so we'll put G over here. And that must be equal to F, which is A times B, quantity inverted. Right there. Cool. How would I prove that this is true? Let's try another one. Here's A prime B or C. What could that be equal to using De Morgan's theorem? Well, I take this prime, I move it inside. I take the plus, change it to times, take the prime, put it on the C. Then I proceed to use the inversion on the inside. I invert both literals to make A or B prime. I still have my C prime out here. I cross multiply. I get AC prime or B prime C prime. And now I take a look at this and I think to myself, is this equal to A prime B or C inverted? That is to say, I did this manipulation using De Morgan's theorem, but how do I check to see if it's true? Is this true? So here's the question mark. Is this true? Did I make a mistake anywhere? How can I verify it? How do I validate this equation other than by using the Boolean algebraic manipulation that resulted in it? Well, the answer is I could do a proof by perfect enumeration. So proof by perfect enumeration says take ABC, write out your truth table. Take AC prime and say wherever A is equal to 1 and C is equal to 0, we're going to put out a 1. So here's a 1, A is equal to 1, C is equal to 0. Here's a 1, A is equal to 1, C is equal to 0. So AC prime comes up with a nice function. This is supposed to be 0 right in here. And now here is another little product term called B prime C prime. And it's going to be true whenever B is equal to 0 and C is equal to 0. So it must be true here, and it is. And it must be true here, and it is. And now I can form the disjunctive form between these two, that is the OR. And if any one of them is 1, the output is a 1. And here, and here. And now I've got a nice column. Let's compare this output, which is from here, with that output over here. So we'll write out A prime, that's A prime B, sorry, A prime B. So that means A is 0, B is 1, so that's going to be a 1. That'll be a 1. Everything else is 0. Now I'll take C, copy it in, 0, 1, 0, 1, 0, 1, 0, 1. And now I go in and I multiply A prime B, I add A prime B ORed with C. Anything there's a 1, I'll put a 1 because it's ORed. And now I have to invert the output because it says here it's inverted. So I take this whole column and I rewrite it inverted. And then I compare this column with that column. They are identical. And that's what I wanted to show. Quod estrum demonstratum. That's what I needed to demonstrate. So this is a way to prove by perfect enumeration that which has been proven by algebraic manipulation. And the interesting thing about Boolean algebra is you can do a proof by perfect enumeration. You can't do that with regular algebra because there's too many different possible numbers. Whereas here, there's a very small countable number of numbers, and proofs by perfect enumeration are possible. And therefore, De Morgan's theorem works, and you can prove that these things work either through algebraic manipulation or by enumeration, proof by perfect enumeration. How's that grab you?
I have a question.
Yes.
So I'm just confused on the last step of your using the De Morgan's theorem. So did you switch? So for your answer, which is in the parentheses A prime, and B or C, is there a prime outside of the parentheses, first of all?
All right. So let's number the steps so we can see where we
Oh,
are.
okay.
1, 2, 3, 4. Which step were you confused about?
Like between how you got from 4 to the answer.
This here?
Yeah, but how you got from that to like what it equals, because I'm just confused.
Why is it equal to this?
Yeah.
because
That's the answer. Oh, okay.
I wanted to, and that's why there's a
Okay.
question mark here.
Okay.
I wanted to
Okay.
validate my proof by using a perfect enumeration table.
Right. Yeah,
And
I
then-
just read that wrong.
And so
I'm
this
sorry.
validated that this equals that by virtue of the fact that the
Mhm.
columns are equal. And
Okay.
therefore, I can check this off and say, yes, I validated it. And you know what it's like? It's like when you try to write, a disk and you think, I think it looks like it's done, but then it goes through and it checks the copy against what was written for the purpose of validation to see if there were any errors during the copy.
Yeah. Okay, sorry. I didn't realize that what you proved at the end, what it equals, was step 1. I didn't realize that at first, but now I get it.
Yeah. So
Thank you.
no worries. No worries. So now we've got 2 ways to prove things: proof by Boolean algebraic manipulation. I have proof by perfect enumeration. And I know that I can always fall back on proof by perfect enumeration, assuming the number of variables is small. Okay. What happens if there's 4 variables, Professor Lyon? Well, then you're not going to have 8 rows. You're going to have 16 rows. And then you say, but what if there's 5 variables, Professor Lyon? Well, then you're not going to have 16 rows. You're going to have 32 rows. And things will become unwieldy very quickly, exponentially so. And if you had 8 variables in your expression, you'd need 256 rows. And you might want to consider writing a computer program to do the proof by perfect enumeration. Now, this is an interesting point because computers do proofs. They do that. They do that. And so what happens is people can't understand the proofs, which is very interesting because now you've got like this magic box that just says, yep, it's correct. And you don't exactly know why. And proofs can be 300-400 pages long. No human being can read that. And there's no insight gained from the proof. So people don't like that kind of proof. But in fact, sometimes that's the kind of proofs people have to deal with because they don't have good ways to prove these things. Why do these lines appear? I don't see them on my see, it's like the automatic gain control. I put my hand there, the lines go away. You guys see those lines, right? What's up with that? How does it work? I've got no clue. See, that's good, right? Yeah, stump the chump. So here's question 13, right? And I like this one because it's showing, geez, look at that. Now it goes away. It's showing duality. So here's duality in action. I have to think for a minute. Is it really in action? It sort of just sits there. It's not really in action. There it goes. Here's duality. Just went by. So then pluses go to times, ones go to zeros, and duality is being applied to both sides of the equation to give us another equation, which is also correct. How do I know this is correct? Well, if x is equal to 1, then x prime must be 0, and 0 times stuff is equal to 0. Because if it didn't, I don't know, my computers would be quantum or something. And then here is x or x prime, and we know anything ORed with 1 is equal to 1. And therefore, if x is equal to 0, then x prime must be 1, and 0 ORed with 1 is equal to 1. In action. Right? Doesn't it feel like action? And that's question 13. Let's do another one. Question 14. More duality. If I took the dual of x or y, then I get x times y. Let's do question 15. I got x or y inverted, and that's supposed to be equal to x prime y prime because De Morgan's theorem. If I take the dual of x prime y prime, I get x prime or y prime. But I need to take the dual of both sides to get an equation that remains correct. So taking the dual of just the right-hand side gives me something which may or may not be equal to something else. And in fact, it would be equal to x times y inverted. Right? So in other words, if you take the dual of this side, it's x, y inverted. Note the parentheses are maintained. If you don't maintain the parentheses, the answer will not be correct. Why? Because you will have written x, y prime, which is not correct. It's not equal to that. So don't write that. Don't do that. So that's a, yeah, here's a good example. X times 1 equals x. We like that, identity. Take the dual, x plus 0 is equal to x, which is very good because if x is equal to 1, we'll get 1. X is equal to 0, we'll get 0. That's question 21. Here's one question. Oh, well, here. How do we know if these two things are equal, right? How do we know if x prime, y prime is equal to x or y inverted? And the answer is proof by perfect enumeration. We've got x, y equal to 0, 0, 0, 1, 1, 0, 1, 1. I have x or y, that's in the parentheses, and I OR these two columns together, and it comes out to be 0, 1, 1, 1. Now I can invert it. Here's the inversion, 1, 0, 0, 0. And now here's x prime, which is equal to 1, 1, 0, 0. Here's y prime, which is equal to 1, 0, 1, 0. And now here's x prime times y prime. So I have 1 times 1 is 1, 1 times 0 is 0, 0 times 0, 1 is 0, 0 times 0 is 0. And I compare these two columns and they are equal. And therefore, De Morgan's theorem works. Thank George Boole. So, good deal. Any questions about this? Proof by perfect enumeration?
Professor, I don't really have a question about the proof itself, but just for clarification, when you're doing the x, the term x or y prime, when you're doing the dual of it, would you say you distribute the prime first and then you would take the dual of it, or does it would you say that's the easier way to go about it?
Yeah, I mean, if you're going to do De Morgan's theorem, right? That's x or y prime. De Morgan's theorem says you distribute the parenthesis, you distribute the apostrophe into, and you take the plus and you turn it to times, and you take the times and turns it to plus. And you take the ones and you turn it into zeros, and you take the zeros and turn it into ones. And you can see that on page 51. I really ought to put a bookmark on that. So here we go. Here we go. So De Morgan's theorem, right? Here is De Morgan's theorem. What do we see? Times goes to plus, plus goes to times, 1 goes to 0, 0 goes to 1, and all the literals are going to become inverted. This is just like the dual, except there's a difference. The difference is you leave the variables alone. So times goes to plus, plus goes to times, 1 goes to 0, 0 goes to 1, and the variables are left alone. So duality looks just like De Morgan's theorem. The difference is you do not invert the variables. So when you look at the dual here, for example, you see all the pluses got changed to times, all the times got changed to pluses. It's a completely mechanistic transformation, put it that way. So that's where De Morgan's theorem comes from. It's the dual with the inversions distributed. Does that sort of answer your question?
Yeah, thank you.
Sure. It's a good question. So then here comes 16 in the homework. And let me just scroll my little copy of the homework assignment over. Yeah, what is the dual of x, y prime or x prime, y? And if you're doing dual, you're asking this question here. And so what you do is you take the plus and turn it to times. You take the times and turn it to plus. But look at what happened here. These product terms are normally computed first. You maintain the order of precedence. If you don't do that, you're going to get a completely wrong answer. So if you start off with x times y having the order of precedence, you got to maintain it when you transform the times to plus. Because now I can multiply x times x prime. I can multiply x times y. I can cross multiply x prime times y prime. And I can cross multiply y prime times y. X times x prime is 1 times 0 or 0 times 1, and that's 0 because things times 0 are 0. And the same thing for y times y prime. So at the end of the day, what you're getting is xy or x prime, y prime. That is the answer to question 16. What do you think of that? Any questions about that? No questions? Really? That's good. That's good. I'm not going too fast, am I? Because before, in the prior class, I was kind of writing everything out, and it was very tedious and all this other stuff. But now I think it's kind of a little better to kind of chug through the material in this way. I think. It's not going too fast for you, is it?
I think it's good.
It's good. Okay. So then let's see now. We got other questions here. There's paper here. Question 23. That's a good one. Let's take a look. Question 23. I'm going to scroll down on my homework assignment and take a look. So this says that a times a plus b is equal to a. Why should that be true? Why? Well, a times a is equal to a times a. A times b is equal to ab. A times a is equal to a. AB is by itself. I can factor A out. So now that's A times 1 is equal to A, and A times B is equal to AB. 1 ORed with anything is equal to 1. This is like having switches in parallel. Doesn't matter which switch is on. If one of them is on, the output will be on. And therefore, it's A times 1. And A times 1 is equal to A. So the answer is A. And so that's the proof of the law of absorption. And the law of absorption is not mentioned here in the book. A times 1 is equal to A. Yes, it is. Yeah, you know what it is? It's this guy. Operations with 0 and 1. But the part about where it's A times A plus B, that they don't, that is not the, they don't show you the law of absorption here. Interesting. Yeah, I looked for it. I didn't see it. So if you find the law of absorption somewhere, you can. I don't know why you need a law out of this. After all, it comes from the basic postulates, right? It's just cross multiplying and then using operations with 0 and 1. Maybe that makes it into a law. I don't know when it's a law. Why is that a law? What happens if I don't make it correctly that way? Did I break the law? Are they going to get me? Will you bail me out? Will you visit me in Boolean jail? I mean, what happens when you break the Boolean laws? I think those quantum computers are breaking the Boolean law. I'm telling, but I don't know who to tell. That's a problem. Yeah, right. I guess Sheriff Augustus Morgan will get them. So then here's a question. Match X prime inverted equals X with the right theorem. So here it is, X prime inverted. 2 wrongs make a right. That doesn't even sound right, but it's true. Because there you invert the inverted and it makes, right? Because what is this equivalent to? X goes into, X is connected to an inverter, okay, which is connected to another inverter, okay, and then the output is equal to X because the intermediate version is prime, and this is X prime prime, and the 2 primes cancel, and you get the original. So 2 wrongs make a right. See, it says so right there. 2 wrongs make a right. What law is that? 2 wrongs make a right. Somebody said 2 wrongs don't make a right, but 2 rights made an airplane. 2 wrongs make a right. It's true.
That is the involution theorem.
That is the involution theorem. Yes. Yes. And then here's question 25. Let's see now. Match A plus B inverted equals to A prime B prime. What theorem is that? You guys have to know this now.
That is De Morgan's theorem.
Thank you, De Morgan's theorem. And here's the dual of De Morgan's theorem, which says the AB prime, that's the left-hand side here, and this says A prime or B. So it says these 2 things are equal, and these 2 things are equal. And that's the dual of De Morgan's theorem. So that's cool. The dual. That's question 25. So that brings us to the end of the homework. Homework number 2. Homework number 2. Are there any questions about homework 2? That's due next week. No questions? Really? Anything that you want to see covered, or any particular questions within homework 2 that you think might be challenging?
Can
So
we do them? Oh, sorry, you can go first.
number 11.
Number 11, let's do that. Number 11. Multiple choice, what is this? What is this? Okay. You know what? I'm going to get a fresh piece of paper because I think that just makes things neater. So number 11 says not A or B equals not A and not B. How do I rewrite this in terms of the Boolean algebraic notation we already know?
Wouldn't it just be A or B prime is equal to A prime plus B prime? Or sorry, A times B prime?
Exactly. And having seen this now in this form, what theorem is that?
De Morgan's.
There it is, De Morgan's theorem again. DMT, dimethyltryptamine, De Morgan's theorem. So there, De Morgan's theorem. And that is the answer to question 11. So writing it out this way might confuse you, but it's just another notation. In philosophy class, they will use disjunction and conjunction. And the inversion form will look like this. And then they'll write well, try it again. Oops. I don't use this form very often, as you can plainly see. This is the first time I've done this in years. So in fact, it is not in the book this way. This is how you will see it if you're in the philosophy class. This is how you see it when you're in this class. So that's the apostrophe. That's the apostrophe. That's the conjunction, which is the same as a product term. That's the disjunction, which is the same as the sum term. And so this is a disjunctive normal form, and this is a conjunctive normal form. Or put it another way, the way the book says it, it's a sum of products. This is a product of sums. And we'll get into that more later. So other questions you might have about this homework?
I was just wondering if we could do it like another example of like multiplying two like and or like or expressions together, like we did like in number 16.
Yeah, let me look at number 16 again. Number 16 asks, what is the dual of? What is the dual? And so what we did was we said, well, it's x or y prime, and we maintain the order of precedence by using the parentheses, x prime or y, and then the plus goes to times. So that was the dual, but you can simplify this, right? Because x times x prime or xy or x prime or y prime y. And then we said, aha, that's equal to 0, and this is equal to 0. And now we have exclusive NOR. That's what that is. But we haven't discussed that yet. So let's do another one. Let's do, here. I've got one for you. I'll get one out of the book. XY or YZ or X prime Z equals XY or X prime Z. Find the dual. Any ideas? Times goes to plus, right? So that's X or Y, Y or Z, X prime or Z. And so that must be equal to X or Y, X prime or Z. Why should that be true? Well, I don't know. What happens if we multiply it out? X times Y times X prime is going to be 0 because X times X prime is 0. Maybe we should do it a little at a time. XY or XZ or Y times Y is equal to Y or YZ times X prime or Z. Right? And now XY times X prime is going to be equal to 0. XY times Z is going to be XYZ. XZ times X is going to be 0. XZ times Z is going to be XZ. Y times X prime is going to be XY, where the X is prime. Y times Z is going to be YZ. And then this will be X prime YZ. Or XZZ, which would be, I'm sorry, YZZ, which would be YZ. Now let's take a look at the right-hand side. I have X times X prime is equal to 0. X times Z is equal to XZ. X times Y is equal to, sorry, that's X prime times Y. And now I have Y times Z. How can these two things be equal? How is this possible? Well, let's take a look over here. That can be written as factor out xz. And now you have y or 1. Because 1 times xz is equal to xz, and y times xz is xzy. But y or 1 is equal to xz, right? Because y or 1 is equal to 1. So I got this whole thing being equal to xz. And what about this, some of this other stuff? Well, look, there's common terms here, right? So if I take this and rewrite it, it's kind of cool, actually, because look how much simplification you get. I get yz times 1 or x prime. But 1 or x prime is equal to 1, so that's yz. So that takes out this guy and that guy, both gone. And now I've got or x prime y or yz. Well, wait a minute, I got yz in here twice. I don't need it twice, I only need it once. So that one goes away. And now, check it out. Xz equals xz, yz equals yz, x prime y equals x prime y. It worked. It worked. And they call this oh, I can't see it here. Here, now you can see it. They call it the consensus theorem. That's on page 52 of your book. So I've just proven, using Boolean algebraic manipulation, the consensus theorem. Isn't that cool? The answer is yes, Professor Lyon. It's very cool. Moreover, the consensus theorem, which is here. Whoa, whoa, the book's falling. Stand by. Everybody's calm. So now, if you want to, you can take the dual of the consensus theorem, which is kind of what we did over here. And then you do the expansion. Then you do the simplification by factoring out. And then you can get your answer so that they are the two, the left and the right-hand side are equal. And then to make it look really official, you write QED. And then if you say quod estrum demonstratum, it sounds really profound because things in Latin always sound profound. What do you think of that? You asked for it, right? You wanted to see more algebraic manipulation. Now, could you do a proof by perfect enumeration with this? The answer is yes, you can. Yes, you can. And there's only 3 variables, x, y, and z. So it's only 2 to the 3 or 8 different rows. Sorry, was there a question? I interrupted somebody. I'm sorry. No questions? You sure? Okay. And what about this homework assignment? You guys feeling pretty good about it? I think we covered most, if not all, of the questions, especially of the different types. So Boolean algebra is an interesting thing because as algebras go, it's slightly different from the algebras you're used to. Normal algebraic expressions have sort of different treatment here. And in a way, it's a simplified and elegant algebra. And the logic that we've seen so far is what we call combinational logic. This course is divided into 2 halves. The first half of the course is combinational. and the second half of the course is sequential. And in combinational logic, we can do Boolean algebraic manipulations in order to be able to obtain truth tables. In sequential logic, we basically are able to build what are called finite state machines, counters, sequencers, things like that. Now, somebody writes, we're supposed to read chapter 2.2 because I didn't understand negative and positive logic. So that's a very interesting question, 2.2. I don't know that that came up with homework number 2 yet. Let me just take a look at 2.2 and make sure I see where that came in. 2.2, negative and positive logic. To what are you referring? Negative and positive logic. Oh, you're probably talking about the NAND gates, positive versus negative logic. Okay, I think this is what you're referring to, positive versus negative logic. And if we look at positive and negative logic, what we see, I guess I can scooch this over under the camera. I'll just fold the book a little bit. You can see what's happening here. He's put a little bubble there and a little bubble there. These bubbles give you a simplification that comes from De Morgan's theorem. That's a NAND gate. That's an inverter. That's a NOR gate. That's another inverter. So this is an AND gate with an inverter at the end, and this is an OR gate with an inverter at the end. And that's what they mean by in the book about negative logic and positive logic. Let's have a look and see how we can do that. I'm going to get a fresh piece of paper. Stand by. There we go. Oh, everything got pushed. There. It's better now. So let's try and do something like this. X, Y goes into an AND gate. W, Z goes into an AND gate. And the output, the output goes into an OR gate. And we call this F. F is now a function, right? This is OR, that's AND, that's AND. And we write F is equal to, and now we can take this circuit and turn it into some algebra. X, Y, or, because it's X times Y, or at the root, W times Z. And that's clear, right? Because this is the plus and these are times. But now let's use negative logic. Suppose an inverter is added to the end of a AND gate. So that says invert the AND. Now let's assume that I can use a shortcut. I'll take the AND gate and make a single gate. I'll call it a NAND gate. That's not AND, NAND. So this I'll call NAND, N-A-N-D. So now, instead of using two different gates, AND and OR, I'm going to do the same exact thing. X, Y into a NAND gate, WZ into a NAND gate. And I'm going to take the whole thing and run it into a NAND gate and make F. Say, well, what's that equal to? How do I write F? Well, F must be equal to X ANDed with Y, inverted because there's a bubble, ANDed with W and Z, inverted because there's a bubble, and then the whole thing is inverted because there's a bubble. But I know De Morgan's theorem. So that says that it's X, Y, parenthesis, prime, prime, or WZ, parenthesis, prime, prime. Two wrongs make a right. So that's equal to xy or wz, which is the same as that. So now instead of using two different gates, I can just use one gate and a little De Morgan's theorem, and I haven't really had to use more than one gate. And in fact, I can get a single package which has 4 of these gates, known as a quad NAND gate, and it's called the 7400, and it's in the stock room. So I can go to the stock room, get one of these things, breadboard it, and make a little circuit that computes this, and I'll only need one chip and not two, and only one gate and not two. And that is how you use negative logic. And it uses De Morgan's theorem. Look, De Morgan's theorem is practical. What a useful theorem. How exciting. Isn't that exciting? And the answer is yes, Professor Lyon, very exciting. Look, I'm sorry if this doesn't get you excited. I'm sorry for you because it doesn't get better than this. Let's do it again because you asked about negative logic, only this time with a difference. Now we're going to take the OR gate and we're going to run it into an inverter. Not OR. And now we're going to take a shortcut and we're going to put in a bubble and we're going to call it a NOR gate, not OR. So this is equivalent to that. But the difference is this is easier to draw. And you can get gates that have this in it directly. So now, Professor Lyon, what happens if you do this? XY goes into a NOR gate. WZ goes into a NOR gate. And then out comes F. What's that equal to? Oh, I don't know. Let's find out. So that's X or Y quantity inverted, right? X or Y quantity inverted, ORed with, right, because it's another OR gate, W or Z quantity inverted. And the whole thing is inverted. And somebody said something about De Morgan's theorem. And so now it's X or Y inverted, ANDed with W or Z inverted, and the plus gets changed to times. And now I have X or Y times W or Z. And that's equal to XW or XZ or YW or YZ. I don't see good ways to simplify that one. So this gives me a completely different answer. And it's really a rather, sort of unfortunate circumstance, because one thing I could have said was, well, maybe I can, get that sum of products that I had from before, but it's not immediately obvious how you would do that. Unless maybe if you started with X prime, Y prime, W prime, Z prime. But in principle, you should be able to do a synthesis that gives you the same example. And we'll have to discuss that at another time because we're out of time. But this is negative logic for NOR gates, and this is negative logic for NAND gates. And just doing a blanket substitution with the NOR gates doesn't get you the same thing as when you the blanket substitution with the NAND gates, which is kind of interesting. So now you've seen, here, I don't know if that got off the screen. So now you've seen what happens with the NOR gates. That's kind of neat. And in fact, if you think about it, that's X and Y, but they're both inverted. And then that's W and Z, both inverted. So what would have happened if I inverted the inputs here? Then where would we be? And the answer is, well, then these would have been inverted. And then this would have been inverted. And then this would have remained inverted. That doesn't necessarily make life better, because then all of this would be inverted. And I don't see good ways to factor this out. There aren't too many common terms here. Not that I can see offhand. So yes, it's negative logic. Yes, it's using the NOR gate, and yes, you can do synthesis with NOR gates, but it's rather different than if you are doing synthesis with just NAND gates. And that's what I have for you for today. It's 3:14, so I think that's about the end of it. Come back on Thursday with questions about the homework. The homework will be due next Monday. And stay safe if you're driving. Drive safe. Otherwise, stay home, because I think it's kind of nasty outside. Have a good day, and thank you.
Thank you.
Thank you, Professor. Have a good day.
Thank you.
Thank you.
Thank you.
Thank you.
I have one quick question
Yes,
on
sir.
the homework.
Yes.
Is it when we were talking about the NAND gates at the end, is that related to number 9?
Let's find out. Number 9. Yes. Using just 3 NAND gates, you can build an oscillator. Yes, that's true. That's true. Because if you take a NAND gate, you know what? A lot of people are going to miss this question because it's a good question. Could you ask this question on Thursday? Because I think others will benefit from the answer.
Yeah, sure. I'll
Thank
remember to ask.
Thanks very much. Yeah, we should definitely cover question 9, because that's a little bit different,
Mhm.
and we should do that.
Right.
Thank you, and have a good day.
Thank you too.
Bye. Thank you.
Thank you.